All right, hello everyone. This is going to be the Lab for Help session. This one should be a pretty straightforward lab, so I'll go through some common confusions and help lay out a lot of the fundamentals so that you can do this lab quickly and successfully. So to go ahead and start, quick overview, what we're going to cover is part one is going to be the ALU, so ALU is the arithmetic logic unit, followed by the RALU, which is the registered arithmetic logic unit. And then we'll briefly cover how to use DADs to automate some of the inputs. So this will be your first instance of making a full program. All right. So to get started with the ALU, an important thing to note is that the ALU is completely synchronous or asynchronous. So what this means is that there's no clock input, and depending on when you change the inputs into your system, it'll automatically change your outputs. So you can see here, this is the block diagram that's given in your lab document. And then I basically added this smaller block diagram above it. So if you look at this table, table one, labeled ALU functions, you basically have four different combinations controlled by S1 through S0. So that iterates through 0, 0 through 1, 1. And the action that that takes. So for example, when S1 and S0 are both 0, you're going to be taking a complement of A. If it's 0, 1, you'll do a bitwise or A or B. So this is the action. This is the equation that describes the action. So again, this ALU is going to be completely synchronous. So immediately when you change these values of S1 and S0, it'll take into account that change and then it'll automatically populate the output of the muck. So for part one as a whole, the inputs are pretty simple. You're going to have a 4-bit wide number A, same thing for B, 4 bits wide, and then 2 bits for your select line, followed by a 4-bit output. So basically, you'll control S1 and S0, A and B to perform these operations. So another thing I'm going to point out is this C out. This is basically your carry output. So this carry output should be selected when the addition causes a carry. And of course, this should only be true when you're performing the sum function, since carry out is only relevant when the summing is being performed. So for example, if you ever select a complement, an or the and function, there's no instance where cout will be true. So therefore, it'll be dependent on S1 and S0. So that take this into consideration when you design your combinatorial logic. So to break this down a little bit further of what will be in this combinatorial logic block is you'll basically be performing all of these actions. So you'll take A and you'll basically negate every single bit. And then F, you'll do a bitwise OR between A and B. Same for the sum, same for the and. This part will be pretty simple. It's laying the foundation for how you can manipulate the mux and combinatorial logic to perform operations. So last thing on this slide, just a note, you will not demo or build this part, and you'll only need to simulate with what you need to prove that the design is correct. Get this out. All right, to prove that this design is correct. So therefore, instead of iterating through all the different combinations, let's see. Yeah, instead of iterating through all these different combinations, only choose certain input values such that you know it'll work. So maybe, for example, for the not, test that, use something like 1010. So when you look at the output, you can see that every single bit is negated. Lastly, you can do something using like debug outputs. So while the actual output of our block diagram is what we truly care about, having F naught, F or, F sum, and F and outputting for our block diagram is also useful in case we have any bugs. So typically this allows us to narrow down a certain operation. So keep that in mind when you're designing your system. And if you're watching this video not in spring of 2025, these tables will likely change slightly, but the concepts will stay constant. So moving on into the next part, we're going to have our registered ALU. So what it does is it takes the ALU from part one, which is in this blue box, and it expands on that. So now you can see we have 3 bits as select lines. So we essentially have 8 operations rather than the 4 we were working with previously. So exact same thing, you're just adding more operations. Next, in this red box, we add registers. So what this does in our overall design is it allows us to latch certain values. So those operations can be performed, and then we can asynchronously change our inputs to cue the next operation. So for example, let's say I want to perform a complement, and then right after I want to perform a sum operation. I can load in the inputs for the complement the number, and then on the clock signal, it'll load from these muxes, and you can think about it dropping down into the register. And now that it's locked in the register, I can change all of these inputs without this being affected. So to clarify, this blue and green box are all asynchronous. So when you change the inputs, the outputs of those blocks will immediately change, while this red block is synchronous or depends on a clock. So these values will not update until a rising edge trigger. So moving on into more detail, what this green box is, it's essentially selecting the input that the operations will be performed on. So you can see there's 4 4-bit wide buses. You have the input bus, which you can think of as being controlled by the user via either switches or your dad's static IO. You have the Reg A and the Reg B bus. So what this actually is coming from register A and loading back into mux A. So this allows us to use values from previous operations and continue to perform and continue to iterate on them. So if I just did a sum function and that output is stored in register A, I can then load it back in and then perform another function by maybe ORing it with something in mux B. So this is really helpful and allows us to write these longer programs using stored values. So the last one is going to be the output bus here, and this is going to come directly from here. So it's not user input and it's not buses from the current registers. It'll be the output bus, meaning this combinatorial logic has been performed on it. And again, these are all the possibilities for our combinatorial logic. And then again, to highlight this table, it basically selects which one of these input buses are going to be used. So if this doesn't make a lot of sense right now, it'll make more sense when we walk through the example and actually implementing this. So this is a table you're going to find at the very end of your lab doc. And what it allows us to do is basically organize a program so we know exactly when and what we should feed into the inputs so that we get our desired result. So in your lab, you're going to have a series of operations you're going to need to perform. In this video, I'm only going to do the one just to show how the table is going to look. But if you understand this, it'll be very easy to add more instructions. So what this part of the lab does is introduce something called a control word. And all the control word is you can think of the collection of MSA, MSB, and MSC. So remember from the previous slide, MSA and MSB control our inputs. And then MSC, which is 3 bits wide, controls essentially which of these actions are going to be performed via the outputs of our registers. So you can see if you isolate these first 3 columns and make them like 7 bits wide, that's kind of our control word. So in this example, we're going to sum 7 and 4. So this $ is used to denote hexadecimal. So when you get higher up, it'll change like A and B and C. So To start, we need to load in 7 to register A. So we need uh, the select A to be coming from the input, right? Because I need to feed this in. So 0, 0, if we refer back to our table, 0, 0 will be coming from the input bus. And this is what we need because we are inputting a value. So you can see this is selecting from the input bus. Right now, we can't tell really what MSB or MSC is. We'll write this as don't cares for now, since we won't be performing an operation, we're just loading things in. Alternatively, you can just, I guess, put 0, 0 here when you actually have to define values for these. So you can see this is the 7 we're loading in. Cin is only really relevant when you're performing addition, but since we control it and it's an input, we just will go ahead and define this as 0. So next, register A and register B. This is what's currently in those registers. And since we just started our program, there's really no way we can know what are in these registers. And for now, we don't really care. So of course, these will be don't cares. And since we defined a don't care for our mux select C, we can't really know what's on our output bus at the moment. So you can think of this line right here as our divide. This will be like our rising clock edge. So anything past this line will be after our system has clocked, which means anything that is currently output of mux A and mux B will then be loaded into registers A and B. So you can see, since MSA is selecting our input, when this clock is performed, this input will be loaded into register A. Since we didn't mess with anything with B we still can't know for sure. Output, same thing. The output will always depend on mux select C. And then of course, this description off to the right is a visual way to show yourself and anyone checking what you're trying to do in this operation. So next, we're gonna load our second value into B. So we're gonna set A to be 0, 1, which if you refer back to this table, we're selecting from the register A bus. So this is considered a hold. So since we currently have the value 7 in A, on the next clock edge, it'll just essentially go back into A, and we need it to stay there so we can perform our operation. And then MSB, we're gonna select the input bus, and we're gonna put 4 on our input bus because this is our second number. And as you, an important thing to note as you go down these rows, basically these two reg A plus and reg B plus will be reg A and reg B. So as you make your table, you do your first row and you make your second row, make sure to copy reg A plus and reg B plus and put them in here. Because the way you can visualize it, if you think about a simulation, what you're doing is asynchronously changing these inputs, but since there's no clock edge yet, these will stay the same. So now at this line, we'll clock. And since we defined A to just get loaded with the same value as before, this will stay. And now this new input will be loaded into register B. And again, MSC is currently don't cares, so we don't care. And then this brings us to our last step. And a lot of students will say, hey, we'll just make kind of MSC our addition. And you can do that. It'll be like 1, 0, 1. And then the result will be on the output plus bus. But the issue is if you try to do it all in one line, there's no way of storing this output to use in future use. So we use this third line in order to store the value. So you can find in a lot of your programs, sometimes this output plus will be insignificant, and we'll kind of see that in the next step. So moving on to this last line, MSA is now 1, 1. So 1, 1 for our muxes is going to be selecting our output bus. So keep this in mind. When the clock happens, anything on the output bus will be loaded into our register A. And then mux select B is 1, 0. 1, 0 is just holding from register B. And then now we can see our operation 101. Here it's going to be the sum of register A bus and register B bus to the output bus, which is what we want. So you can see now we have our 7 and our 4, which again is the same as reg A plus and reg B plus. And now we have our desired output. So when this system is clocked right here, since we defined output bus to register A, this gets jumped into register A, and it basically overwrites this previous value. So this is the result we want. And you can see now we have our desired value and register B holds, and we have this last output 111 on our garbage output. So this is because although we wanted to sum these two numbers and we ultimately get that results, MUX-C, all it's thinking is it doesn't care about the clock. It's just always summing the values of A and B, since that's what we did. So you can see if you add this, which is 11 to 4, you get 15. So we actually don't really care about this. It'll appear on our output bus, but it'll never get stored. So that's maybe something to note if you see some interesting things in your waveforms. So now we're going to do a quick waveform demo and see how we can actually apply this. So let's see. The last part of the lab will ask you, instead of flipping switches, which is somewhat in the past now, we're going to utilize this waveform software to essentially flip the switches for us. And so this is kind of our first form of automation and program writing. So we're going to use something in this lab called patterns, and we'll also use something called static I/O. So static I/O, you can see, are 31 different things. And since I don't have a DAD hooked up to my computer, it's using this demo. So you can see right now it's all on LEDs or outputs. But if we need to switch something, we're going to go here and use a switch or a push-pull switch, which is basically what we know is 1 and 0. So another thing to keep these organized, if you go to view and then toggle names, you can see they all toggle a value you can define. So let's say I hook my 0 input output up to the clock. I can call that clock. And this maybe is just some other input 1. We'll switch this back to a switch. And then now I can kind of see what I'm doing here. So this is a more manual way to do it, but still doesn't require you to wire up your switch and LED circuits, which of course is a time saver. But now we're going to head over into patterns and see how this can all be done kind of automated. So we start in patterns. And if we go back to our PowerPoint real quick and kind of look at our outputs, so the things that we control are, of course, this control word, which is 7 bits wide, and this input, as well as a clock. So when we make this waveform, we'll have to decide all of those. So I'm going to start just by adding a signal. I don't have a current circuit wired up, so I'll just use an arbitrary value. Here, we'll just call this our clock value. And this will be clock right here. And in the lab dop, it specifies 0.5 hertz, which means it'll clock once about every 2 seconds. So 500 hertz or 0.5 hertz is the same as 500 megahertz. And you can see right here on the time base, it clocks at 1 second and then it clocks at 3 seconds. So now we'll start by adding our control bus. So again, this is arbitrary. We just need 6 input outputs. So let's do one more here. Oh. All right, so let's just say we use these. We'll add this, and if you click here, we can actually rename it. So maybe we'll call it control. And we'll add a our last bus, which needs to be a bus of 4. Let's just select these 4. We'll call these our input. So now we have all these values, and the challenge here is how are we going to configure these to produce the values we want. So we're going to start here, and it'll be TS. And what we want to do is change this type to custom. And then our parameter, we're going to keep this as 500 megahertz as well. And then for our inputs, we're going to put those same settings on custom 500 megahertz or 500 millihertz. Sorry. So yeah, 500 millihertz is the same as 0.5 hertz. So now what we're going to do is we're going to kind of assign the values we did in the PowerPoint to these, and you'll see how it'll cycle through. So our first control word in this first column is for sure 0, 0. And since the rest of these are don't cares, I'm just going to make them zeros for now. So we'll start with our control. And if you do click this, I guess pencil, and we're going to define our samples as we need 3 samples because we have 3 rows in our table. So if we expand this, we're going to change these. So since everything's going to be 0, this first row looks great. And now for the second row, 0, 1, and we'll just make the rest zeros. So we'll go 0, 1, 0, 0, 0, 0, 0. So nice. You can see this loads in perfectly. And then the last row here for our control word is 1, 1, 1, 0, 1, 0, 1. So 1, 1, 1, 0, 1, 0, 1. You can see all these fields get populated. And you can somewhat ignore 32 and 85 because it's essentially the decimal representation of these 7 bits. So now if you look at our waveforms, you can see it loaded into our correct values. And then now we would do essentially the same thing for our inputs, which would be 0 or 7 and then 4. So I'll just go ahead and do that real quick for this example. Let's define, we need 3 samples again. So originally we need 7. Just make this 0. And then 4, which is just a 1 here. And then the last row we don't care about. So now you can kind of see how this will perform. So this is automatically feeding all these values into our system. So that now we don't even need the static IO, manually changing these and then clocking it when we're ready. So when you actually implement this on hardware, you'll see the hex to 7 segments light up. It should go through your programs. You should be able to view register A and register B, and then as well as your output bus. So I guess now that we did that, I'll add another thing to this table is, so if you're loading in 2 different discrete values, you need 2 rows. But let's say we wanted to sum 4 and 4 together. A quick trick to actually condense that into 1 row is you can say MSA is 0, 0, and MSB is also 0, 0. So at this clock edge, this input value will get loaded into both A and B. So that'll save some time. Of course, just like normal programming, you can get the desired result in a lot of different ways. Some may be more efficient than others, but you'll learn that doing your lab. So that's going to be the end of this video. I hope you found it helpful. Any questions can be directed into the Slack. So thank you very much.